The birthday paradox says if you have 23 people in a room, there's a 50% chance that 2 of those individuals out of the 23 share the same birthday. If you don't think into that too far, it doesn't make sense, right? Like, wait, 23 people, there's 365 days in a normal year. That's how you get to that point where it's a 50% chance. So the joke is you go to a pub that's got like 30 people in it, 40 people in it, and you say, hey, random person sitting at the bar, I'll bet you a beer that 2 people out of this bar full of 40 people share the same birthday. And you're hoping they say, 40 people, there's 365 days in a year. Oh, you're an idiot. I'll take that bet. Because otherwise we'd have something called duplicate initialization vectors. And there's a cryptography attack called known plaintext attacks. In fact, if you go way back to the world of WEP, wired equivalent privacy, that was one of the issues is somebody would use a tool like Aircrack NG. They would disassociate you from the network. You join back on again, but that's okay because I know what it looks like in a plain text form. And I use your MAC address to populate in the values. And now I've got the known plain text that corresponds to the resulting ciphertext. You can see monkey has the same hash each time. But if we change that to monkeys, it's got a completely different hash. We use hashes for things like password security or password storage.
Everyone, it's David Bombal back with the amazing Steven Sims. Steven, great to have you back on the channel.
Yeah, great to be back. I like that we're doing this more often now.
Yeah, I really appreciate you making the time and, sharing your knowledge and expertise with all of us. Just for everyone who doesn't know Steven, Steven's been a hacker for many, many years. He's also one of the authors of this book, fantastic book. But Steven, really important to highlight. You created a YouTube channel. It's been a while now, actually. So perhaps you can tell us about this YouTube channel and, why you created it. Just for everyone who's watching, please go and subscribe to Steven's channel. I think it's a fantastic channel. I get a lot of pushback sometimes about, David, you're just doing basic stuff. But Steven, you've done advanced stuff, but you're also doing a whole range of other stuff on your channel. So perhaps you can just tell the audience about your channel.
Yeah, for sure. Thanks. I started it off about 2 years ago now. And actually, David, you were one of the first people to reach out after the channel, I think, was only live for a month or two. And that really helped me out, of course, to get some visibility. So I always appreciate that. A lot of times on YouTube or other broadcasting networks or platforms, whatever you want to call them, that there wasn't as much or isn't as much advanced content as I had hoped to see out there. And having been teaching for a long time, I get, of course, a lot of people saying, hey, I can't afford to go to a training class, or I'm looking for certain content that I just can't find out there, whether it be browser exploitation or kernel exploitation or fuzzing and all kinds of other topics in the vulnerability research space. So that was kind of the initial goal, was to get back to the community and provide either from myself or from a lot of guests that I have on their expertise to share that with the public.
But you don't just do advanced stuff, you do a whole range of stuff now, right?
Yeah, I started it off really wanting to focus on nothing but vulnerability research, but it actually expanded out. I've had experts come on to talk about blockchain and smart contract security, ICS security, the web side of things. So we just had one the other week on multi-factor authentication bypass for doing internal pivoting. So mostly on the offensive side, but I also like to have some people on occasionally from the forensic side, especially so attackers, we often think that we're very quiet, that we're like ninjas moving through the networks. But in actuality, it's usually due to the fact that they're not really watching their logs very well. And we're not, in fact, very quiet. So it's helpful to get the deeper or forensics perspective so that we can lower our footprint a bit.
I'm glad you mentioned crypto, right? That's what we're talking about today, but it's not the crypto that a lot of people might mistake this for, right? Correct?
Yeah, and this came out of the last session we did on the dark web, and we were looking around at some things, and I think I was demonstrating some stuff using GPA, the GNU Privacy Advisor, and PGP or GPG, and how your OPSEC needs to be really strong, and how some people lack fundamental or foundational knowledge about cryptography, which is so important if you want to obviously do anything from protect your data to securely converse with someone or many other things.
And I mean, I think it's really important to highlight, you've got to know the basics, right? Before you can, some people just want to run before they can even crawl. And I mean, cryptography is such a basic part of the world. Like you said, it's, the whole world runs on this stuff, private and public keys and asymmetric, symmetric encryption. I'm hoping I'm not jumping the gun here. I'm hoping that's the kind of stuff that you're going to explain.
Yeah, absolutely. Like you just said, a lot of people don't understand the basics, and it's really important to know the very basics and how it all works and how it all ties together. I mean, something as simple as a key exchange or a digital signature can be quite confusing to folks. So it's a good one to walk through.
So I'm going to keep quiet now and give it to you, Stephen. A lot of the audience complain if I interrupt you, so please take it away and I'll ask some questions along the way. But looking forward to this.
All right, so I didn't know what title to give to this presentation, so I'm just calling it Introduction to Cryptography. But of course, we'll talk about the security ramifications and considerations as we go through things. So the items that we're going to be covering are, we'll look at some basic cryptography. Obviously, this is not going to cover all of the things. There's so much to cryptography that we just don't have time to get into. But I want to talk about some of the basic forms of encryption that oftentimes are mixed together into an algorithm to provide that confidentiality that we want. So we'll talk about some basic items like XOR and substitution ciphers and rotation ciphers. And then again, those things are all mixed in together to create some efficient algorithm. After we get through the basics, we're going to talk about the two primary types of cryptography, meaning symmetric key or single key cryptography. And then we'll jump into asymmetric key cryptography, which is a two-key system. Underneath symmetric key cryptography, there's two primary categories. One is block ciphers and the other one is stream ciphers. So I'm going to draw onto the screen as best I can. I'll warn you that my drawings I'm not a very good artist when it comes to that. So I'll do my best. And it really does help explain things when you're drawing one component at a time while you walk through. So that's why I chose to do some of the explanations via presentation. You'll see I put some diagrams together, and other ones I'll be drawing on the screen to be able to talk through things more clearly. Then again, we'll get into asymmetric key cryptography, also called public key crypto systems, which we typically use to generate or share the symmetric key that's used to encrypt the data during the session. And I'll get a little bit more into why we do it that way when we get to that section. And then we'll talk about digital signatures. That's something that I think confuses a lot of people. I'll mention PKI briefly, but we're not going to go down that rabbit hole because that's a whole nother thing. But we'll talk about what a certificate authority does when it comes to digital signatures, because we want something called non-repudiation, which basically means if I encrypt, I don't have to encrypt it, but if I send you something and I want you to be able to validate that I am the one who sent it, it's all based on the protection of this public-private key pair that we'll get back into. If we want to add something like a certificate authority, that gets into this web of trust. I'll talk briefly about that as well. That is when you have someone else vouching for you. So just because I say that I'm some actor, I'm Brad Pitt, and I'm communicating to you, and if I can trick you into thinking that that's true, and we use cryptography and I sign it, you might believe that it actually is in fact from me. But if we don't have anyone vouching for us saying, hey, I know that in fact that really is Brad Pitt that you're talking to, then obviously we lose a little bit of security there, credibility there. In order to understand digital signatures, we have to understand hashing. So we'll look briefly at some hashing examples and how that factors in. I've created some pretty, I hope, decent diagrams to help explain this. And then at the very end, I want to mention something called steganography briefly, which is how we hide and embed or inject or substitute data inside a host file. So not only are we getting that confidentiality because I've encrypted something and I'm not sharing the key or the passphrase, I'm also maybe hiding that encrypted data into a host file so that you don't even know that something's there. My quick analogy, and I may say this again later on with steganography, is like if you came into my house and you saw that I had a giant safe sitting in the corner of the room and it was locked, you don't know what's inside of it, but you know that I'm hiding something. With Stego, my analogy would be that I actually hide that in the wall and I put a portrait or a painting over top of the safe so you don't even know that it's there. That's kind of what we get into with steganography. And I'll tell you some examples of how Stego is used and who the biggest users of Stego are. So first off, basic encryption examples. Again, this is not complete. There are so many different variations of things. I'm not a mathematician. I know that the funny joke is that math is a 4-letter word. And I know some people say maths. Some people say math, so either 4 or 5 letter. Some people stay away from that their entire life, just like some people stay away from learning how to program their entire life. And as someone who works in the offensive space, I think in this day and age, it's really important, as a defender as well, that you have some level of programming or scripting experience. And I say the same thing about cryptography, because if you're a pen tester or a red teamer or someone just assessing a cryptographic implementation, as long as you have some foundational knowledge, there's nothing that should be preventing you from being able to assess that implementation. And as someone who is reviewing or assessing an implementation, a cryptographic one, we typically don't have to get into the world of mathematics. There are, of course, crypt analysts out there and others who are taking a look at the algorithms or the ciphers that have been created and the mathematics behind it and try to look for some type of vulnerability or weakness in it. But again, when we as a community consider a cryptographic algorithm secure, that's typically done by way of years of public intense scrutiny. So it's not like some company says, hey, we created a great new algorithm, you should go use it. It's typically everything about it is transparent and it's public and anyone can review it and assess it. And when you have years of brilliant mathematicians and cryptanalysts studying it and trying to break it and they don't find something, then that's when we tend to deem something to be potentially secure. And then at some point, as computing power ramps up even more and more, something called the key space that I'll talk about as we get into some of these examples as well, needs to be taken into account, because the greater the key space, the harder it is, or harder it should be for someone to do like a brute force style attack to try to guess every possible key in the key space, which would then, of course, let them decrypt your data. So we'll get back into that type of stuff as well coming up. But let's start off with a very basic example, which is XOR, or an exclusive OR. This is a Boolean logic operation. You might have heard things as well like and or. From a reverse engineering perspective, you might see an instruction that says test, and then it says a register, like the contents of a register, against the number 4. And what that's actually doing, that test instruction, is a bitwise AND operation. So a lot of times we'll have data shown as in something like a bit mask. Think of something like a TCP flag. So in communications over TCP IP, in the TCP header, we have these flags like SYN and ACK and PUSH and FIN. That's working as a bit mask where the ordinal bit position within that array, each of those are flags. They're indicative of something. And if it's a 0, it's off. If it's a 1, it's on. So we can see if the SYN flag is on or off. And if we do something like a test, we're actually checking to see if a certain bit within that bit mask is on or off. And then we make a decision based on that result. So this is another example of a Boolean operation. When it comes to cryptography, we use XOR or XOR, however you want to pronounce it, to take two inputs, which are going to be ones and zeros, but we only take two inputs. And then from those inputs, we produce a result. And that result's either going to be a 0 or a 1. You may have heard of things like truth tables as well. So the word cat, C-A-T, in all capital letters, that is ASCII. When we represent that in data, we use something called an ASCII hex table, or the hexadecimal representation. And I'm going to jump over to a Linux system here real quick just to show you how you find this. So let's take a look at the ASCII table by typing man or manual ASCII. And what that brings up here is the ASCII table. And you can see, look over to the far right. I'm going to highlight that @ character, the @ sign. Next to it, you see 40. So 40 is the hexadecimal representation of an @ sign. And then in decimal, that's 64. So when you saw cat on the screen, you saw C and then 43 next to it. 0x, which means hexadecimal or base 16, and then 43. An A is 41. And then if you go down to a T, that's hex 54. So that's where we're getting this from. C is 43, A is 41, and T is 54. Now in binary, if you were to take a calculator, and this is in scientific mode or programmer mode, if we go and take a look at base 16, and I know it's probably tiny, but if you bring up the Mac or the Windows calculator and you choose base 16, and then we can enter in hexadecimal 43. So automatically when we enter 43, again, it's really small, but below that in binary, it shows you that value. And it says 1000011. And if you look on the screen over here to the bottom left, 1000011. And that's the letter C. So these are the different numbering systems. We've got base 2, which is binary, base 10, which is decimal, and base 16, which is hexadecimal. And in computing, we need to learn how to read all of those. You might hear somebody say everything's ones and zeros on the computer, but in fact, like opcodes and things like that on Intel or another processor architecture like MIPS or ARM, those opcodes are typically represented in hexadecimal, as well as the operands and the operand values. But at its core, you can certainly convert base 16 over to base 2, which is binary. And you can look at this data and have it represented in different numbering systems as you see fit. But back to the point, if we want to take the letters CAT, capitalized, which is cat, and we want to see its representation in the ASCII chart, hexadecimal, you can see it's 43 for C, 41 for A, 54 for T. And then if we represent that in binary on the bottom, you can see we have CAT and the binary representation directly above those letters. And this is important when we're doing something like XOR, because remember, XOR takes in 2 binary input and it produces a 1-bit binary output. So if we drop down, here's an example of encrypting with XOR. And some people, you might have heard it before, people say perfect encryption. When somebody says perfect encryption, in my experience, what they typically mean is someone has like a run book or some kind of a book where you have a copy and someone else has a copy, and there's only 2 copies of this book in existence, you hope. And on each page is going to be a key. And that key, let's say it's represented in binary. So in our example here, we want to take the word cat, as you can see up top in green, and then we want to XOR it against the key. In this case, it's dog. When we are doing something like using stream ciphers and generating a key stream and using XOR in these operations, we typically want the key to be equal to the length of the data that we want to encrypt. So in this case, we want to encrypt cat. So we're going to get an equal length value to XOR against that, which we're choosing dog. So you can see in blue is the binary representation from the ASCII character set of dog, and it's equal to the length of cat. So if we want to encrypt this, we would then take the 2 inputs, one at a time, and we produce the output. So with XOR, if the values are the same, if it's a 0 and a 0 being XORed together, or a 1 and a 1 being XORed together, that produces a 0. So over on the right, if we XOR 1 from the first bit in cat against 1 from the first bit in dog, that produces a 0. Because again, if the numbers are the same that you're XORing, it produces a 0. If the numbers are different, like if it's a 1 and a 0 or a 0 and a 1, that produces a 1. So if we were to go through this, and we're not going to go through every single bit, of course, and we start on the left, we'd have a 1 and a 1 being XORed together, producing a 0 because the numbers are the same. Then we've got a 0 and a 0 being XORed together, which produces a 0 because the numbers are also the same. Same thing with the next 2 over. So we're producing nothing but zeros at the bottom. And then the next one over, it says 0 against a 1. Since the numbers are different, that's going to result in a 1. And in fact, the next 2 values produce 1s as well because the numbers are different. We would go through this with all 3 words in this case all 3 letters represented in binary. And you can see at the bottom, if we were to take this binary value, which is 0000111, and represent that in hexadecimal, it would be the number 7. Now you can use a calculator and do this much faster. And we're not going to go through how to convert numbering systems by hand so much. But if you were to start on the right in binary, the far right would be the 1's position, then the 2's position, then the 4's position, 8, 16. And as you go left, you keep doubling that value, its representation. So if we start at the right, that's the 1's position and it's on. So we take that 1. We move over 1 bit, that's the 2's position and it's on. So now we've got 2 plus 1, that's 3. Then we go over 1 more bit to the left and it's on, and that's the 4's position. So we have 4 plus 2 plus 1, and that's where we're getting that 7 from. We do the same thing over here in the middle one and the same thing over there on the right. I'm not sure why Cyphertext decided to let the T go off to the right there, but that's fine. It's supposed to be 1 word. So I'm calling this our ciphertext because let's go back to that example where I said this could be perfect encryption if we never use the key again. Pretend that you received the data in the red. You intercepted it somehow, like a messenger had it in their hands and you seized it. And now you have that binary or that hexadecimal representation of the binary and you want to decrypt it, but you don't know what the key is. You don't know that the key was dog. You could try every possible value and XOR, try every possible key within the key space and XOR that encrypted data against it, you would then recover plain text. But how do you know if you got it correctly? You might get back the word car or bat or tar or many other 3-letter words. You would never know that cat is the right one unless you knew something about the message or you were able to compromise the key that was used. So if we go back to the example of that run book and we've got pages in it and we've got one duplicate set. So I've got a copy and David has a copy. And I say, David, I'm sending you a message. Or maybe I don't even tell him and he receives a message. And he knows that no one has used the current key that's on the first page of our run book, which is dog in this case. So he knows to use dog to XOR against that encrypted data. And the same way that we XOR to encrypt the data, we reverse it to actually recover the data. So again, since David receives the encrypted data, which we put up here in the red, and he knows that the dog key has never been used, he writes that out in binary and then does that same XOR operation. So the 0 and the 1 produces a 1. The 0 and the 0 produces a 0. So remember, if the numbers are the same, it produces a 0. If the numbers are different, it produces a 1. He's able to XOR the encrypted data or the ciphertext against the key of dog, and he recovers cat. And now what we would do is we would burn that page in the run book and we'd never use it again. And on the second page would be the next key that we're supposed to use. And let's say David encrypts something and sends it to me. I receive that data. I know now to use the key that's there in the run book. I burn that page. And that's why some people have called it perfect encryption, because it's one time. You're only using these keys one time and then you're never reusing them. But hopefully I didn't overcomplicate that at all. And it's
That's great.
You understand basic XOR operations and how we can use that for cryptography. Now, most of us would never rely on XOR alone as a way to encrypt things, but it is an important part of many crypto systems out there. With stream ciphers, you'll see soon when I explain it, we generate something called a key stream, and then we XOR that key stream, just like we are here, against the plain text to produce the ciphertext. Again, a lot of components, but it's really, if you dumb it down and simplify it, it's actually not that complex when you don't get into the really advanced mathematics behind advanced block ciphers like AES and the Randall algorithm. So another example is going to be arbitrary substitution. Now, there are different types of substitution ciphers out there. I'm just going with a simple one here called arbitrary substitution. And what you see here is A through Z or A through Z, all 26 letters of the alphabet. And then I've arbitrarily mapped each letter to another letter in the alphabet, but you can only, in my example, do it once per letter. So since we're mapping A to R, we can't map any other letters to R, because then it starts to complicate things. Now, absolutely, there are different types of substitution ciphers out there that do allow you to use multiple letters, or multiple letters can use the same letter. There's lots of tricks you can do to make this harder and harder. But this is basic encoder. So down at the bottom, you can see I want to encrypt monkey, the word monkey, using arbitrary substitution. So as long as David has a copy of my arbitrary substitution mappings, he'd be able to decrypt anything I sent over. So if I were to send this over to David, DESPLU, he would say, okay, a D, what does that map to? And we could say a D right here is mapped to an M. So I know that D becomes an M, which is the first letter in the word monkey. Then we go to the second letter, which is E, and we find E in the mapping. E maps to O. So now we recover MO, and we do this each letter until we get to the end of the message. And now David, in this example, is able to recover monkey. Now, this alone as well certainly is not enough to be a good crypto system. But imagine if you mixed arbitrary substitution, also XORing the data against another key, then you start to make things more complex, more difficult to recover. Another example would be rotation ciphers. Instead of arbitrarily mapping one letter to another letter in the alphabet, this is called a rotation cipher. You might have heard of Caesar cipher before. That's a ROT3 or rotate 3 cipher. You could rotate any number that you want. We could say rotate 20. All we're doing is taking the letters in the alphabet and we're rotating it forward whatever number is used as the key. So 3 in this case is the rotation key. We're saying take the letter A, rotate it 3 letters forward. So A becomes B, C, D. B becomes C, D, E. C becomes D, E, F. So as long as you know what the key is, in this example, monkey becomes what you see over there on the right, PRQ, NHB. Because we would go to the letter M and we say M rotated forward 3 is P. And that's why that M becomes a P over there. And then O rotated forward 3 becomes R. And that's why you have the R over there. So it's another way of encrypting something. The problem with this is the key is in the name of the cipher. Rotate 3 is literally telling you the answer. But again, imagine if we use this and combine this with a substitution cipher, with XORing, and now using rotation. And if you ever went to a computer science program at university, if you've taken a certain class, they might have had you write your own encryption algorithm, or they might have you go through how an algorithm like DES works. And when you do that, you start to realize, oh, they're mixing the columns, they're substituting things, they're doing some of these exact techniques that we're talking about in a way that makes things overly complex and difficult to decipher. Another example would be permutation. And permutation is absolutely another thing that we can factor in as a way to increase the security of our algorithm. So in this one, we're reordering the position of the letters. And as I said with arbitrary substitution, there are different ways we can do permutation to make things more difficult. We're looking at basic right now. So if we take the word alphabets right there, and you can see above it, I've got 1 through 9, and that's the ordinal position. And that's in plain text. That's what we want to encrypt. That's the clear text message. If I want to encrypt it, I can scramble the position, and this would be my key. So 9416732885. Now, if you had this key, you would be able to recover the data, but if you don't have the key, you can't. So if David were to receive this message, which is at the bottom in red, and he has the key, he now knows that this first letter, if you apply a key to it, actually becomes the 9th letter. And then this 1 right there, the A becomes the first letter. 2, L becomes the second letter. So we can recreate alphabets just by doing this mapping to the position and then unscramble it. So as I've said a couple of times now, imagine if you apply arbitrary substitution, rotation, permutation, and even XOR all together, you're starting to create an encryption algorithm. And again, it's like a kid's decoder ring if you ever heard of one of those things before. So I think that takes us through kind of some basic examples of how we could start encrypting our data to provide confidentiality. Any questions from you, David, on that?
That's brilliant, man. I love this.
All right, cool. Let's go into symmetric key cryptography then. So we're kind of moving ahead and we're jumping forward here a bit. Symmetric key cryptography, remember our goal. We want to provide confidentiality. I want to make it so if I encrypt something, I encrypt a secret message and I send it across the internet to David, that no one else is going to be able to recover that or read the contents of the message unless they have the key. Now, there's something called a key exchange. We'll get back to that soon. But in this example with a symmetric or one key crypto system, the same key is used to encrypt data that is then used to decrypt that data. This is where we really have to protect the keys. I remember back early on in my days when I was a network engineer and working in security, we would have to set up a VPN tunnel. So we'd typically just get on the phone and we'd say, hey, let's use this as the key. And as long as no one was like tapping that phone call and eavesdropping, then no one else knows what the key is. Now, the key, just like a password, you want it to be strong. You don't want it to be something simple that people can guess. And you want to rotate that key periodically, often as possible, actually. And a lot of technology nowadays, rekeying is done automatically, constantly. And as long as the rekeying is done securely and no one can break that exchange and the way in which the keys are being generated or shared, we should be good. It's not a good idea to share the key over a phone call and then enter that into a router or router and have that be the key used to protect our data. But that's the way we used to do it in a lot of cases. Another way we might do it is use like PGP and we encrypt the key. And then as long as I encrypt with David's public key in this example, as long as his key isn't compromised, his private key, he can use his private key to decrypt that. Now that's getting into asymmetric key cryptography. We'll get back to that soon. Let's take it back here for a moment and simplify it. If I select a key and I encrypt my data using a particular cipher or encryption algorithm using that key, the ciphertext that's generated should not be readable by anyone else unless they know what the key is. Now, certainly they could guess what the key is. They could try to brute force through the key space, which is why we need to make sure that our key space is large enough. If you go back to like an old example like DES, Data Encryption Standard, came out in like 1975, a long time ago. I believe the first example of DES was only 56-bit encryption. And then you may have heard of triple DES, which gets us up to 168-bit encryption. So it's much stronger. We use multiple keys. That key space, increasing the size of the key space, is really what we're counting on to make it so it's going to be hard or difficult for someone to try to brute force all the possible keys in the key space. And I'll explain that more when I show you an example of how stream ciphers work. But again, to take a step back, I encrypt data with a key. David has a copy of this key. He can then decrypt the data with that same key. So it's really important that we protect that key. So I'm going to do some drawing now, and I apologize that my drawing skills are not great, but I think it should be helpful. I'm going to explain the difference between stream ciphers and block ciphers. These both fall under the category of symmetric or one-key crypto systems or cryptography. So we'll start with stream ciphers. So let me jump over to my drawing pad here. All right. So I'm going to start off by drawing a circle, and that circle is going to serve as our cipher. And we're going to put in stream. So this is our cipher. Now, examples of stream ciphers, RC4 would be an example of one. I believe A51 is one, and E0 for things like Bluetooth and others, GSM. So we need to create a key. So my example here, I'm going to type out key equals, and now I got to create a key. This is where something like the key space is going to come into play. I want to make this example pretty simple so that we don't overcomplicate things and I'm not drawing way too much. But let's say it is 64-bit encryption, which we would not want to use. We want at least like 256-bit encryption, but I don't want to write out some massive key. So let's say it's a 56-bit encryption or a 64-bit encryption, but I'm going to make 24 bits of that, something called the initialization vector. And we're going to get back to that here in a moment. So that means 40 bits for the key, and that means 24 bits for the initialization vector. So we're going to call the key maths. So we'll put key equals maths. This is the key that we would then need to really protect, because if David and I want to communicate, we both need to know the key. And if that gets compromised, obviously someone's going to be able to decrypt our data. So this key would be much stronger than this in the real world. So that's going to be our key. I'm going to create something called an initialization vector now as well. So let's take this up here and I'm going to type IV. IV stands for initialization vector. This is a very important component in stream ciphers and in cryptography in general, because we want to make sure that we don't encrypt the same thing twice in the exact same way. If I encrypt the word monkey 100 times using the same key and the same cipher, the ciphertext that's produced should not be the same each time. If it is, we've got a problem with our crypto system. But the problem is that if we're using the same key and the data going into the stream cipher is the same every time, it's going to produce the same ciphertext. So we need to introduce something that changes the key every time I encrypt something. And that's going to be our initialization vector in this example. Since I said our example is 64-bit encryption, it's actually 40-bit encryption. And that's why I've got 5 bytes, because 5 times 8 is 40. Our key is math. That's the key. But we're using the initialization vector 24 bits or 3 bytes as part of the key. But this typically isn't considered something that's secret about the key. And the reason for that is, imagine if I use the key maths to encrypt something and I send it to David, he goes to decrypt it, but oh no, he doesn't have the IV, which is a portion of the key that I use for that very specific encryption. So I need to get the initialization vector over to David that I used in order for him to be able to decrypt the data. So oftentimes that initialization vector is sent over to the recipient as a clear text attribute, or maybe it's encoded, but it's not supposed to be secret. So it's not really part of your key, even though it is when you're encrypting the data each time. It's just not a secret part. So I'm going to say my key is 3FC. That's my IV portion of the key. Now we're going to get back to that. And let's say what I want to encrypt is the word monkey, since I've been saying it. So that's the data I want to encrypt. So I'll say plain text. Now, at this point, let's say we want to encrypt this data. So what we're going to do is we're going to take maths in as input, and we're also going to take that initialization vector. So it's basically going to be, in my example, maths 3FC as the key in this example. So that's what we're sending in as maths, which is the key that's secret, 3FC, which is part of the key for this encryption, but it's not secret. We're also going to take, you would normally think that an encryption algorithm or the cipher is going to take the data, which is monkey in this case, in as input, and it's going to go through those examples that I described, like permutation and substitution and mixing and all that, and it's going to produce a ciphertext. But with stream ciphers, we actually take the length of the data that we want to encrypt, and then we generate a key stream that's equal to the length of the plaintext data that we want to encrypt, and we use that XOR operation that I talked about earlier. So instead of taking monkey in, we take the length of monkey. So I'm going to go ahead and say, let's put this down there. And in this case, the length equals 6, because monkey is 6 bytes. And that ends up going in as input. So again, it's not the word monkey that's going into the cipher. It's the length of the word monkey or whatever we're encrypting. So one more time, we've taken in the key, and concatenated with that key is the initialization vector for this specific instance where we're encrypting. We take in the length of the plaintext data, which is 6, and that's going to produce something called a key stream. So let's go over here, and we've got key stream. Now, if we didn't use that initialization vector and we encrypted monkey 10 times with the key of maths, the key stream is always going to be the same. And we don't want that because that breaks the encryption. We'll talk more about why that in a moment. All right, let's say that the key stream that's produced. Now, normally, if we're actually generating a key stream for the length of 6, that's likely going to be 6 bytes of binary that's going to be produced. I don't want to overcomplicate this thing. I don't want to write out 6 bytes of binary. So I'm going to write 6 bits of binary, and we're going to pretend it's 6 bytes. So let's pretend that the key stream that was generated is 011010, and that's 6 bits, right? Now, remember we talked about XOR before, a little bit earlier, and we say if we XOR and the numbers are the same, the input numbers are the same, like it's a 0 and a 0 or a 1 and a 1, that's going to result in a 0. But if the numbers are different, then it produces a 1. So we're going to XOR the key stream against the plain text. Now, let's pretend that the plain text is 111010, and that represents, remember the ASCII chart I showed you and how we did that mapping with the calculator? Let's pretend that the ASCII value of monkey is 111010. We just generated a key stream, which is 011010. And that key stream was generated based on the key maths, the initialization vector 3FC, and the length of 6 in this case. And the length is important because remember, it generates a key stream that's equal to the length of the plaintext data that we want to encrypt. And then we use an XOR operation. So just like before, I'll draw a little line here. We would go in and we'd say if the numbers are the same, that produces a 0. If the numbers are different, it produces a 1. So the first one we're going to do is 0 against the 1. Since the numbers are different, that produces a 1. 1 and 1, the numbers are the same, that's a 0. 1 and 1, that's the same, 0. Actually, all the rest of them are zeros. This is the encrypted data that I would send across to David. So 1000000. Now, again, imagine if you're the attacker and you were sniffing the traffic and you saw 100000 go across the wire. You don't know what the key stream that was generated is in order to be able to recover the plaintext. If you did know the key stream, all you have to do is XOR the key stream against the ciphertext and you recover that plaintext. It's that simple, but you don't know what the key stream is. Now, if you compromise the key of maths and you know what the initialization vector is, then of course you'd be able to generate the same key stream and we'd have a problem here. Let's do the reverse real quickly, just so everything makes good sense here. So if I'm now David on the other end, I need to generate the key stream. In order to do that, I need to know the length. Well, that's easy. Just read the length of the ciphertext. So that's an easy one. I also need to know the key, which is that shared secret, where if that's compromised, it's game over. Let's pretend it's not compromised, so it's not supposed to be. But David also needs to know the initialization vector that was used to encrypt Monkey, because that's part of the key for that encryption, and he doesn't know it. So in actuality, when I send that data, however I do it, over to David and that ciphertext, I need to include the IV as some kind of plain text attribute so that he knows to concatenate it with the key of maths. So remember, that portion of the key space is not secret. The greater the initialization vector size, the smaller the key space of the actual key. The greater the key itself, the smaller the key space for the initialization vector. And the IV, again, is used so that we don't encrypt things the same way each time. We want that key to be unique every single time. So I send over the ciphertext and I send over the initialization vector to David. He can then use that initialization vector to concatenate it to the key and then generate the same key stream. So David would generate 011,010, which is the exact same key stream. And again, we'd have our XOR operation that we want to do. So just like before, if the numbers are the same, it's a 0. If they're different, it's a 1. So right now we're saying 1 and a 0 against each other. That's going to produce a 1. 0 and a 1, 1. 0 and a 1 is a 1. 0 and a 0 is 0. 0 and a 1 is 1. 0 and a 0 is 0. So notice that matches the plain text right there. I'm holding it up next to it. See that? We XOR'd it back and it matches the original plain text. So earlier I said we wouldn't want to rely on XOR alone. But in this case, we're generating a unique key stream each time because we're using the same key until we rekey it, but the initialization vector gets changed each time. So if I go in again, and let's say I encrypt Monkey a second time. Well, in this case, the initialization vector is going to change. So we come up with a new one. Let's say it's 238. Now, this IV would be the one used the next time we encrypt data. In this case, if we encrypt Monkey twice in a row, the first one was 3FC with maths. The second one's 238 with maths. So see how the key is technically changing? And what that's going to do is going to make sure that the key stream that's generated is never the same. Even though the key is the same, the length is the same in this case. As long as that initialization vector changes, which becomes part of the key for that specific encryption instance, the key stream will always be unique. And this brings up a really important question, which is, what's the best way to handle the management of the initialization vector? In this case, we've got an initialization vector field that's 3 bytes. That's 2 to the 24th power. At some point, we're going to exhaust the key space of the initialization vector. In order to keep things secure in that instance, we have to rekey by the time the initialization vector pool is exhausted, because otherwise we'd have something called duplicate initialization vectors. And there's a cryptography attack called known plaintext attacks. In fact, if you go way back to the world of WEP, wired equivalent privacy, that was one of the issues. Is somebody would use a tool like Aircrack NG, they would disassociate you from the network, you join back on again. And we know, like on a Windows system, for example, the very first packet that's going to go out, we know what it looks like. It's a DHCP packet, most likely. Things like ARP packets and DHCP packets are always the same. The only thing that changes inside of them is the MAC address. But that's layer 2 on the OSI model. That's not encrypted anyway. So we know what values to populate into that template DHCP packet type. What am I saying here? I'm saying if I knock you off the network, you join back on, and you send out a DHCP packet, it's going to be encrypted from my perspective. But that's okay because I know what it looks like in a plain text form. And I use your MAC address to populate in the values. And now I've got the known plain text that corresponds to the resulting ciphertext. Just like when we XOR the key stream against the plain text, we get the ciphertext. Guess what happens when we XOR the plain text against the ciphertext? We recover the key stream. So in a known plain text attack scenario, I know what the DHCP packet looks like. I know what it looks like encrypted because you sent it out and I sniffed it. I XOR those together. I recover the key stream that's associated with that initialization vector, which is a clear text attribute. So if I ever see a duplicate initialization vector, I'm able to then recover plain text that I shouldn't be able to recover because the encryption key was the same. Even though I don't know the key, I know the key stream of that key with that associated initialization vector. So the question then becomes, what's the best way to handle the initialization vector? Do we want to randomly select it out of the 2 to the 24th power key space, or do we want to sequentially select it? Now, the answer always sounds like random, right? Random is usually the right answer, but in this case, it's not the right answer because of something called the birthday paradox. The birthday paradox says if you have 23 people in a room, there's a 50% chance that 2 of those individuals out of the 23 share the same birthday. If you don't think into that too far, it doesn't make sense, right? Like, wait, 23 people, there's 365 days in a normal year, and you're saying 2 people out of 23, there's a 50% chance they share the same birthday. That doesn't make any sense. That's because they're not thinking about it properly. If you were to put all 23 people in a circle and you drew a line between every single pair so that everyone has a line connected to everyone else, we fully mesh it, that's how you get to that point where it's a 50% chance. So the joke is you go to a pub that's got like 30 people in it, 40 people in it, and you say, hey, random person sitting at the bar, I'll bet you a beer that 2 people out of this bar full of 40 people share the same birthday. And you're hoping they say, 40 people, there's 365 days in a year. Oh, you're an idiot. I'll take that bet. When in fact, once you get from 23 people up to 40 people, you're up at like 80, 90% chance that there's going to be a match, that there's going to be a pair. Similar to like roulette. When you play the game roulette, you go to a casino and you see the numbers 1 through 36, and maybe there's a 0 or double 0. When the croupier spins the ball and drops in 16, they usually put like a signboard or a placard up next to the roulette wheel. And that's to like trick people. It's to take advantage of people because people will see, whoa, 16 hit twice in a row. What are the chances of that? Well, it's the same chance of 15 hitting after 16, right? Like, why would it be any different? Sure, there are variables. There are factors such as the wheel speed and velocity of the ball and the croupier, all that stuff. But without factoring those things in, it's just as likely for 16 to hit a second time in a row than it is to 15 or 0 or something else. And we don't actually remove that number from the wheel once it hits. And that gets us into the birthday paradox problem here with our key space of 2 to the 24th power with initialization vectors. I can't remember the exact number, but it's like 10,000 or something. Every 10,000 or so tries, there's a 50% chance that a randomly selected IV out of the pool of 2 to the 24th power is going to be a duplicate. So by doing it sequentially instead of randomly, we know that we've never had a duplicate. And we also know that when we exhaust the key space of 2 to the 24th power, that we need to rekey at this point, because at that point, every single IV is going to be a duplicate. And just remember that one thing again. We could say, well, if we don't want to rekey often, can we increase the size of the initialization vector pool? So like 2 to the 32nd power. The problem there is you're reducing the actual key space itself. It's going to make it easier for someone to brute force that. You could increase the size of the key, but then you're decreasing the space for the initialization vector, meaning that you need to rekey more often. If you take a look at something like WPA2, the wireless protocol, that actually creates a transient key based on some master key based on the passphrase that's protecting it. And that transient key during the handshake that's selected is only used for a short period of time. There's actually an initialization vector that gets set to 1, and then it sequentially goes up, and sometime before it hits FFFF in hexadecimal, it's supposed to rekey again. And it keeps doing that automatically for you, which was a great improvement from the old WEP that was out there. Then WPA3, of course, you get into asymmetric key cryptography that's used that we'll talk about here in a moment. There was an attack that came out, it was probably 8 or something years ago, but it was called the crack attack. And somebody found out with WPA supplicant that you could actually replay, I think it was step 3 in the WPA handshake before the initialization vector pool got exhausted, and it would rekey to 0. So the key would actually become 0. So old Android phones and things like that were very vulnerable to that type of an attack. And that goes back to my point, which is, or one of my earlier points, which is a lot of penetration testers and red teamers and others avoid cryptography because they're worried about mathematics being involved. But it's usually not the maths that we're going after. It's usually a poorly implemented crypto system, because oftentimes a developer of an application or something that doesn't quite understand crypto well enough to implement the crypto system securely. And we've seen that time and time again. Proprietary implementations are pretty poorly done. You want it to be, tested publicly and scrutinized before we deem that secure. So hopefully that explains a little bit as to how, when you look at symmetric key cryptography, how stream ciphers work. And again, there's always variants of these things, but at its basic form, the stream cipher takes in a length, it takes in a key with or without an initialization vector, it generates a key stream that's then XORed against the plain text to produce the ciphertext. And as long as no one has compromised that key, or you don't have a vulnerability in your crypto system, and you're properly handling and managing the initialization vectors, you should be secure.
That's brilliant.
All right, so now we're going to switch from stream ciphers under symmetric key cryptography to block ciphers. And we'll also talk briefly about block cipher modes, which are very important. So I'm going to draw here, let's say AES. So that's going to be our cipher, our encryption algorithm. It's the Raindahl algorithm, but it's the advanced encryption standard. And before, the cipher took in the key as an input, and it took in the length of the data to produce a key stream. Typically, in block ciphers, the cipher itself is actually encrypting the data using some of those examples we talked about earlier, like substitution and permutation and rotation and others. So let's go ahead and generate our key. I'm going to call our key is, we'll just say math. Obviously, we'd want it much better than that. And then we're going to actually create some data here. So let's create something that I want to encrypt. So I'm going to say I space love cryptography. I'll put some exclamation points in there. I want to make sure it's long enough. That's why I'm using those exclamation points. So let's move.
I was expecting you to say Bitcoin, man.
Bitcoin. I don't have any right now, so I don't love it. All right, so AES is a 16-byte block cipher, unlike DES and triple DES, which are 8-byte block ciphers, which becomes important with things like padding, but we're not going to get into padding today. So since it's a 16-byte block cipher, and it's a block cipher that we're using, we can't have it be a random value like we were able to do with a stream cipher. In a stream cipher, it doesn't matter the length, because the length is an input and the key stream is generated that's equal to the length of the data that we want to encrypt. In a block cipher, we encrypt based on the block length. So we have to make sure that what we're encrypting meets the block length. And since AES is a 16-byte block cipher, let's see where we're at. So we've got I, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So right there, I want to put some spaces to separate that. And that's our first 16 bytes. Let's just check that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and then we get over to our second block. 1, 2, 3, 4, 5, 6, 7. So since it needs to be 16 bytes, we now need to add 9 bytes of padding to make it equal 16. Now, if this were PKCS padding, like PKCS 7, the number that we would use to pad, or the value that we would use to pad, is the literal number of bytes that we need to pad out. So in this case, it's 9. So we would put 9 bytes of 9s, and that's what we would be encrypting. This is going to be our block 1, and over on the right is going to be our block 2. Now, as input, we would then take block 1 into the algorithm along with the key of maths. So those are the two inputs. Again, it's not the length of what we're encrypting. It is the literal first block of plain text. And what that's going to produce is ciphertext block 1. So if we go up here, we'd have ciphertext block 1. And that would be something scrambled. I'll just put a bunch of bytes in. Pretend that that's 16 bytes. Next, what would happen is we take block 2, and it would go in with the same key. Now, that should already concern you, because remember before we talked about an initialization vector in stream ciphers, and that's going to make sure and prevent that if the data is the same, if block 1 and block 2 are the same, that it's not going to produce the same ciphertext block. In this example, though, since we're using the same key, but the data is different in block 2, ciphertext block 2 would be different. But a lot of times, let's say that we're encrypting a whole hard disk image. there's going to be a lot of repeating blocks of zeros. And if you were to look at that like a histogram, or you were to just visibly look at that, you're going to see lots of encrypted data that's exactly the same. And that's because the blocks of plaintext were the same and there was no initialization vector that was introduced. But in this example, since our data in block 2 is different than block 1, ciphertext block 2 is going to be something completely different. We're going to pretend that's 16 bytes. That's at its most basic form. That's what we're doing in a block cipher. We're not going into the actual algorithm and the mixing and all the permutation and stuff, but we're looking at just from a high level what's going on. We simply take in block 1 with the key, we encrypt it. Block 2 with the same key, we encrypt it. Block 3, block 4, and we keep doing it until we encrypt the entire contents. Remember what I said though, and that is, if block 1 and block 2 were the same, pretend they were all zeros, that means the ciphertext block 1 and ciphertext block 2 would be encrypted, but those two blocks would be identical, which is a problem. We want to make sure it's different each time. We have to offer some uniqueness. Now, there's different block modes that you can use. One example is electronic codebook. An electronic codebook, that's the worst one. It doesn't use an initialization vector, so therefore what I just described is exactly what would happen. Same key, block of data. Same key, block of data. With a different mode like cipher block chaining, we introduce an initialization vector to start making this a bit more secure. There's other modes as well. There's various open feedback modes. There's counter mode. But let's walk through one example, and that would be, let's do cipher block chaining mode, block cipher encryption, to see how we could make this a little bit more secure. So instead of electronic codebook, we can use something called cipher block chaining. This diagram I just put up here is a way for me to explain it and show you how this is a much better option with regard to confidentiality than ECB mode would be. So up at the top, let's pretend that plaintext block 1, block 2, and block 3 are identical. It's all zeros or whatever you want it to be, but it's the same. Instead of simply taking that plaintext block and then encrypting it, producing a ciphertext, what we do now is we first XOR it against something. That something is an initialization vector, just like we talked about with stream ciphers. The important thing here is that the initial initialization vector that we use needs to be created thoughtfully. It shouldn't just be zeros or something arbitrary. We should know that it's going to be unique each time. It's only used for the very first block in the chain here. So say we want to encrypt something that's only 3 blocks in length. The first block of plaintext would first be XORed against the initialization vector, which is equal to the length of the plaintext block. And then we encrypt it with our cipher, producing ciphertext block 1. Now, when we get to block 2, which is the same as block 1 in plaintext, we don't XOR it with that same initialization vector. Instead, we XOR it with ciphertext block 1, making it unique as an input into the AES algorithm in Cypher, producing ciphertext block 2. Then again, with plaintext block 3, what we're XORing it against is unique compared to block 2 and block 1. Therefore, what's going as an input to encrypt to AES is going to be, in fact, unique, resulting in a brand new ciphertext block 3 that's different from block 2 and block 1. Now, this is a great option, but one of the things people like in cryptography is speed as well. And in this example, we have to run things serially. We can't run them in parallel because we're dependent against a prior operation to be able to continue downstream. But it is a more secure option. As I mentioned before, there are other modes, though. There are things like counter mode, which does allow you to do things in parallel. There's different types of feedback modes. You can actually combine modes together. And anytime you see something like AES-CC, something, some letters, that's usually the mode is what it's referring to there. So that's the difference between block ciphers and stream ciphers under symmetric key cryptography. And all these things have to be taken into consideration. These are questions where if you're assessing a crypto system or you're performing a risk assessment, you want to ask these types of questions because just one example, you know that electronic codebook is not as good as a block mode option as something like cipher block chaining. So jumping back to the slides, in these examples with asymmetric key cryptography, I actually created diagrams that are going to be hopefully easy for us to digest. I like to actually draw them out when I'm talking about symmetric key cryptography, especially with stream versus block and the modes, because I think it's more helpful to piece them together. But with asymmetric key cryptography, I think we have a good option here, a good way of going through these slide diagrams that I created. So a couple important things to say first. Symmetric key cryptography is a single key system, as we saw. The same key is used to encrypt that we use to decrypt and vice versa. With asymmetric key cryptography, it's a two-key system. So in this example, I've got Steve on the left on the bottom, and we've got David on the right on the bottom. Notice that each of us generates a public-private key pair. Now, those public-private key pairs are protected via a passphrase that we would then have to remember or enter in to be able to access those keys. Typically, we are not as protective, well, almost always we're not as protective over our public key as we are the private key. You might have heard of something like a PGP key ring, and maybe we have a group of people who work together, and on my key ring, I've got the public key for all the other members of my group, and they have my public key. Because how it works is when you encrypt data with one key, it's only its pair, it's only its other part, which would be the private key in this example, which would be able to decrypt that data. So if I encrypt with your public key, the only key that can decrypt it is your private key. If you encrypt with my public key, the only key that can decrypt it is my private key. You cannot use the public key to decrypt something that was encrypted with the public key. And the same thing with the private key. That's why it's a two-key system. Now, the key space required to be able to support these asymmetric key cryptographic algorithms are much larger than a symmetric key crypto system. There's actually some good charts you can go out there and Google for, and it will show you. I think the smallest in comparison, meaning the closest in size for an asymmetric key cryptographic algorithm to that of a symmetric key algorithm, is ECC, which is the elliptical curve crypto system, depending on which type you use. But of course, there's Diffie-Hellman, there's RSA, and there's different mathematics as in relation to how it all works. A lot of them use very large factors. We take things like massive prime numbers and we multiply things together and we get the product. And it's a question about how do we know what numbers were used to come up with that product. And I'm simplifying things greatly, but I'll show you an example. In this example here on the slide, though, let's say I encrypt something with David's public key. I send it across to David across the untrusted internet. Then again, the only key that can decrypt that data that was encrypted with his public key is his private key, and vice versa. We typically don't ever encrypt something with our private key unless we're signing something. We're going to get to that soon. We'll talk about hashing and how that works in a moment. So let's look at a quick example with some maths and hope that I don't make a horrible mistake here when I'm computing this. This is going to get a little bit complex, even though I'm going to give you a very basic example. I'm giving you an example of how Diffie-Hellman could work. And what we want to do is use asymmetric key cryptography to generate the symmetric key that's going to be used to encrypt data during our session. Now, that's something I forgot to say. We can absolutely encrypt using asymmetric key cryptography. I can encrypt something with your public key. You could decrypt it with your private key. But that's not typically how we tend to use it. We use asymmetric key cryptography to exchange or generate the shared symmetric or secret key that we're going to be using for the duration of a session. And even in something like PGP for pretty good privacy, when you're sending messages back and forth, you're actually encrypting a symmetric key with the recipient's public key. And they can then decrypt that to then decrypt the data. So we're not encrypting the message with the recipient's public key. We're encrypting a symmetric key that they can then use to, they can use their private key to decrypt that symmetric key to then decrypt the data that I sent that was encrypted. So it doesn't typically work quite how you think it does in most cases. So again, asymmetric key cryptography, we typically use that to generate or share the symmetric key to be used during a session or to encrypt something. So let's talk about how we could potentially generate a key. My goal is for David and I to somehow generate the same exact symmetric key that we're going to be using to encrypt data back and forth across an insecure or unsecure network, meaning there's adversaries eavesdropping. So I'm going to simplify this a bit. And again, I'm not a mathematician, but this should work pretty well. So I'm going to say we're going to generate a prime number. So I'm going to say select n equals, and a prime number is a number that's divisible by 1 in itself only, right? So I'm going to use 809 for my prime number. We also need to create something called a generator number that is related to the prime. If you want to get into the details as to like how and why the prime and the generator are selected, there's great articles out there that you can go and Google for. But just know in this example, we need a prime number, which is a number that's divisible by 1 in itself only. Now, in the real world, this would be a very large prime, like a Racine prime. It's a huge, huge number. And then the generator is usually a simple one that is able to cover much of the space needed when using that prime number. But sometimes it's a very simple number like 2. I'm going to use the example 733 as our generator. And now we need to do a couple things. On the left side is going to be my side, and on the right side, it's going to be David's side. So over here, I'm going to say Steve, and I'm going to say choose XA. What this XA, or actually I'll call it XS to make it more clear. XS as in Steve. So the S is not some fancy math thing. It just means Steve. X is going to be my private value that I never share. So I'll say, let's compute XA. Now, I wouldn't normally represent it like this. I would use super or subscript, but I don't know how to do that in preview, so I don't even want to bother trying. And I meant to put S there. S stands for Steve. Okay, this is my private value. And the number I'm going to choose is 9. What I need to then do with that is I need to calculate YD. And D is going to be the public key value that I want to actually send over to David. So I'm going to call it YS actually to keep it consistent. So XS is my private value that I'll never share. YS is my public value that I'm going to send over to David. But I need to generate that. So to do that, we would take the generator number, we'd raise it to the power of my private value, which is XS, and then we'd mod it to prime, which is 809. So that's the calculation. So I'm going to need a calculator to help me do this, of course. And the number is actually going to be, generator is 733, raise it to the power of my private value, and then mod it to prime. That's the calculation I want to make. Okay, so we want to do 733, which is a generator, raise it to the power of 9, which is my private value, and then mod it to 809. So I'm going to use a Windows calculator for this real quick because I don't know where the mod option is on the Mac calculator. So we're going to say 733 raised to the power of 9, mod it to prime. Look how big that number is right there. Mod it to prime, which is 809, and we get 802. So over here, we'll just write our answer. So YS equals 802. So that first calculation is done. This is my public key value that I would send over to David. So let's now do the same thing, but over on the other side. Now we need to select a private value for David now as well. So we're going to say, David, choose X. This time I'll say D for David equals 11. That's the private value. Obviously, it'd be something much larger than this in the real world, but I want to keep the math kind of simple here. Same thing as before. We want to calculate the public key value. So YD, and that same calculation, G to the power of X, D, which is David's private value, mod it to prime like that. I could just say N here if we want. Down here, we're going to say 733, which is the generator, raise it to the power of the private value, which is 11, mod it to prime, which is 809, and that should give us YD, or David's public value. So let's say 733 to the power of 11, mod 809, 733 to the power of the private value, which is 11, mod prime, 809, and we get 18. So 18 is the public key value that's sent across from David to me. So this is where our first exchange here would happen. So we take this value, send it over to that side, and we take this value and we send it over to that side so that we can do the rest of the calculation. Now that we have each a public-private key pair, we've exchanged the public keys. Now, take a step back. On the internet or where the adversaries are, they'd be able to see 809 as the prime, they'd be able to see 733 as the generator, and they'd be able to see the public values going by. The calculation and the privacy is completely dependent upon the protection of the secret key values on each side. So I'm going to go ahead and write up the next portion of the calculation here. what we're hoping happens now is that we can generate the exact same symmetric key on each side. So we're going to say key, and I'll put S. That's going to be the secret key or symmetric key for Steve. And that calculation is going to be, we take David's public value that was sent across, we raise it to the power of my private value, which is 9, mod it against prime. So that again is going to be 18, raised to the power of private value, mod it to prime, 809, and we should get our answer. So let's go back over to the calculator again. So that's 18 to the power of 9. 18 to the power of 9, mod it to prime, which is 809, and we get 315. So let's go back over here. Key S equals 315. That's our symmetric key. What we're hoping is that when we run the same calculation using my public key on David's side, that we get the same value. If we do, then we just shared a symmetric key securely, and we should be good to go, and no one should be able to generate that unless our keys get compromised. So I'm not going to write everything out again. I'll just write the equation we need to do. We need to take my public value, which is 802. We need to raise it to the power of David's private value, which is 11. We need to mod it to prime, which is 809. And what we're looking for is KD equals, let's see what it is, 802 to the power of 11, 802, raise it to the power of 11, which is David's private value. And then we mod that to prime, 809, and we get 315. So we see that it works. When you look at that, and I'm sure there's mathematicians, if somebody's watching this who knows math very well, they're like, oh my God, the way you wrote that out just makes me in a lot of pain. And I completely understand. I'm trying to deal with the limitations of my drawing skills mixed with the app that I'm not used to using. But hopefully that makes sense. Remember, we created 809 as our prime number, 733 as our generator. Steve selected 9 as the private value. David selected 11 as his private value. Those should be protected, never be shared, never be let out. And they're protected via something like a very secure passphrase that gives you access to those keys. Then we came up with the calculation for the public key value in this case that we want to share across the untrusted network. So again, we took the generator, raised it to the power of the private value, mod it to the prime number, and I got 802 on my side. We got 18 on David's side. Those get exchanged. We then use those values in the calculation to come up with the symmetric key. So on my side, I took David's public value, raised it to the power of my private value, modded to prime. We got 315. David takes my public value, which is 802, raised it to the power of his private value, modded to prime, 315. So therefore, we now have the symmetric key to use for the duration of this session. And there's not many moving parts in that math. I mean, that's again why a lot of times we don't spend our time trying to pen test or assess the mathematics behind everything, because the fewer the moving parts, hopefully the more secure things are. That being said, I think that's a good example of a key exchange, which is going to get us to our next part here. So digital signatures. So far, we've looked at basic cryptography. We've looked at symmetric key encryption, which is a single key system. And within that, we saw block ciphers and stream ciphers. We also then talked about, of course, asymmetric key cryptography and how we typically use that to share or generate the symmetric key that we're going to be using for the duration of a session to have that confidentiality. Because we like to use symmetric key cryptography since it's a single key system and it's faster. But we use the asymmetric key cryptography to exchange or generate the symmetric key to use. But then we get into something called non-repudiation, which is how do I know that I'm talking to David? How does he know he's talking to me? If I can convince him that I am who he thinks I am, then I can sign it and he can then feel confident that it must have come from me. But again, no one's vouching for me. That's when we get into public key cryptography and that web of trust. But in order to understand digital signatures, we have to talk about hashing briefly. So to explain hashing, I'm simply going to go over to a VM, and what we're going to do here is hash a couple things. So if we were to look at our Etsy shadow file, so if I say sudo -i, and we say tail/Etsy shadow, you can see the user account dead list right there. And then we see this $6 $. That 6 is the hash identifier. So there's a table out there that tells you which hashing algorithms use based on that identifier. It could be something like MD5, SHA-1, SHA-256, and many others. Then between the second $sign and the third $sign right there, that's something called a salt. And that value between the $signs, what that does is it adds some uniqueness. It's almost like an initialization vector that we talked about. Let's say that I have the same password as David, and we both have accounts on this system. This hash that's stored here, that's the actual hash of the password. If David's password and my password are the same, the hash stored should be different. And the way we ensure that it's going to be different is that we fold in this salt value into the equation. So I have a unique salt, David has a unique salt. Even though our passwords are the same, when we hash that password, our salts are different. Therefore, our resulting hash is going to be different. So if we want to hash something, basically it's a one-way transformation. You cannot take something that's hashed and turn it back into the input that was sent in the first place. And I can explain this very easily. If we were to do something like use the DD, and I say DD input file equals /dev/urandom. I hope the urandom's there. We'll find out. And we say output file is going to be /temp/temp.bin. And we say count equals 100, block size equals 4,096 bytes. I need to use IF. So what I just did there is I created a file of random data that's that size right there. And if I then say, take that file and we pipe that in as input to SHA-1 sum, permission denied. Interesting. Let's take a look at that. ls/temp. I'm just being lazy and changing that real quick here. So if we send that in as input to SHA-1 sum, so what I've taken is the contents of this temp.bin file and I've sent it into SHA-1 sum, which is a tool that uses the SHA-1 hashing algorithm to generate the message digest or the hash itself. So this right here is a representation of the contents of temp.bin in its current state. As long as that file does not change or the contents of that file does not change, that hash will always be the same if we run it again and again and again. See, it's always the same. But if we were to change one single binary digit inside that file, a completely unique hash would be generated. And it's the same thing if we do something simple, like say, echo the word monkey, and we pipe that into SHA-1 sum. You can see monkey has the same hash each time. But if we change that to monkeys, it's got a completely different hash. We use hashes for things like password security or password storage. We use it for forensics. So we'll do something like an acquisition of a hard drive image. We'll use multiple hashing algorithms to hash the contents of that hard drive image to prove that nothing has been changed, that the data has not been tampered with. We would do that initially during acquisition, and anytime we go to access and take a look at that data and we show up at court. So it's proving that the data integrity is intact, that no modifications have been made to the contents of that file. It's a fixed size output. So at the one example, I'm sending in a 7-character word into SHA-1 sum, and it produces that. And in another example, I'm taking the contents of a file that's quite large, and that's going into SHA-1 sum. It's a different value, but the length is the same. It always produces the same length output. Same thing here. If I say echo monkey, and we pipe that into MD5 sum, if I can type, and we do it twice, you can see it's the same length. Now notice that the SHA-1 sum was larger though. So if we say echo monkey into SHA-1 sum, see how it's larger? It's a 16 bytes or 20 bytes? It's 16 bytes. MD5 is a 16 byte hash. SHA-1 is a 20 byte hash. So that's why you're seeing a difference in the length here. The point I'm trying to make is that if you take a 10 gigabit hard drive image and you were to send it through the MD5 hashing algorithm, it's still only going to produce a 16 byte output. There's no way to reverse that. You can't take 16 bytes of output and recover a 10 gigabit hard drive, a 10 gigabyte hard drive image. It's just not possible. So that's why it's called a one-way transformation that we use for things like data integrity. So I know I probably didn't give the best, most streamlined example of how hashing works, We didn't go into the mechanics of it. It gets pretty interesting, actually. It starts off with these static registers, which then get folded into the algorithm, the one-way transformation. Everything's based on a block size, just like we talked about with AES, but I think the block size is 512 bytes. And then if what we're trying to hash is larger than what can fit into a single MD5 block size, we then take the hash of the first block and we use that hash as the registers to hash the second block. And then we continue on and on and on. And that's why everything always ends up as the same size at the very end. And there's no way to recover anything from it. The only way you can try to do that is if you were to guess what the input was and you get the same resulting hash. Now, there are techniques known as rainbow tables that you can use to try to speed things up. And that's why we add salts into the equation. With salts, rainbow tables lose most of their value. But if you're not using salt, something like a rainbow table could actually speed up and determine what something like a password is rather quickly. The reason I wanted to explain hashes, though, briefly, is because this is what we're going to be using as part of our digital signature or in that operation. So let's jump back out. And I broke this up into multiple pieces so we can go into each phase. So remember what we're trying to prove now. I'm trying to show non-repudiation. I'm trying to sign what I'm sending you so that you can trust that it came from me or whoever owns that private key. Remember earlier I said we typically never encrypt anything with our private keys. We decrypt something that was encrypted with our public key with our private key, but we typically don't encrypt things with our private key. One exception to that is when we want to have non-repudiation in digital signatures. We take the plain text message. Okay, so let's pretend that this message over here is what I want to send to the recipient. Now, of course, I want to encrypt it with, in this case, we're not dealing with symmetric keys. So I want to encrypt this message with the recipient's public key. And now I've got the encrypted message. I know that the only key that can decrypt that is the recipient's private key. But now I want to sign it and I want to prove to them that I am the one who sent the message. And in fact, we can sign things without encrypting it. That's also fine. We're not using a certificate authority in this example. The next thing I'm going to do, and this is why hashing was brought up, I'm going to take that plain text message that I just encrypted in its unencrypted form, and I'm going to run a hashing operation against it. Just like you saw, I echoed monkey into MD5, and I produced a hash of monkey. I'm doing that with my message. So we would select a hashing algorithm like SHA-256. I would hash the plain text message, and now I have a hash for that plain text message. Remember, that is data integrity. That's a hash of the data in its current state. And now I've got a hash of that message. The next thing that I do is I encrypt the hash of the plain text message with my private key. And now we've got the encrypted hash that was encrypted with my private key, meaning the only key that can decrypt it is my public key. And we've got the encrypted message, which I encrypted with the recipient's public key. The only key that can decrypt it is the recipient's private key. We send these things over to the recipient. The recipient takes the encrypted message. They use their private key. They decrypt it. And now they have the plain text message. The next thing they do is they take the plain text message that they decrypted. They run it through the same hashing operation like SHA-256 that I used on my side. And they create a hash of the plain text message. The last thing they do is they take the encrypted hash that I encrypted with my private key. They decrypt the encrypted hash with my public key, which produces the resulting hash. If those two hashes match, we have non-repudiation because that's how I signed it. No one's supposed to have access to my private key. So I encrypted the hash of the message with my private key. You're counting on the fact that no one's compromised that private key. You decrypt the hash with my public key, and you check to see if it matches the hash that you calculate once you decrypt the original encrypted message with your private key. Now, I'll say one last thing on this part, which is we don't have a certificate authority. If I can convince you that I'm Brad Pitt, like I joked around and said earlier, then even though I'm signing it, I may not really be that person. So we use a certificate authority that we trust to vouch on our behalf. We create things like X509 certificates. And basically, we're counting on the fact that someone like VeriSign or Entrust or others have this root certificate authority that's offline, that's protected, has not been compromised. And we can just like I used my private key to encrypt the hash, the certificate authority can encrypt something on my behalf with its private key. Anyone out there can use the certificate authority's public key to decrypt that. So if the certificate authority encrypts using its private key something that I've generated, it's vouching on my behalf. It's saying, yes, I know that in fact is the right person. I made them show me their ID and all that good stuff. I vetted them. And I am signing using the private key of a certificate authority or a subordinate certificate authority so that when you then decrypt that certificate, that stamp with the certificate authority's public key, and you can check to see, hey, that certificate authority vouched for me. I really am Brad Pitt. You have much more security at that time. Now, of course, the certificate authority can be compromised, but we'd have some really big problems if that were the case. The last thing we're going to talk about in this cryptography walkthrough is going to be steganography, and mostly just because I think it's pretty cool. Steganography, as I explained earlier, is that example where if you came over my house and you saw a safe in the room and it was locked, you know I'm hiding something, but you don't know what the contents are. But if I hide that safe in a wall and I put a picture over it, you now don't even know that I'm hiding something. So it makes it kind of sneaky. One of my first real world, beyond kids using Stego to hide messages from their parents, use cases that I saw, actually it was a couple of them. One was that back when 9/11 happened in the United States and the trade towers were taken down with the jets, it was indicated, but it was withdrawn at some point, so I don't know if it's true or not, that terrorists were using steganography to communicate with terrorist cells. They had a website with a photo of, let's say it's something like bin Laden, and it's always the same photo. But what happens is the web admin keeps embedding secret messages in that photo and uploading the same photo over and over. So intelligence agencies that are watching that website, they just keep seeing the same photo. But when in reality, the contents of it are changing somehow. And if the terrorist cells know to download that and they use a steganography tool to take out the encrypted message that's embedded in and they decrypt it, they can communicate that way. There was another example in Australia with the Australian Federal Police where there were criminals, I'll just say looking at illicit images, and everybody knows what I'm referring to there. They used steganography to hide illicit, illegal images inside legal images. So who would think that someone's hiding pictures and the pictures that are hiding inside are illegal? And it was a law enforcement operation where they were able to determine that these files were steganographically altered, and they used a tool like Stegalizer to extract the contents that were encrypted. Then they try to crack the encryption, the key, to be able to decrypt the contents. So a lot of times criminals are who use steganography. It also gets used by like digital watermarking and stuff like that, gets into Stego a bit. Now, how does this work? This is one example. There's generation Stego, there's injection Stego, there's replacement Stego. I'm going to use an example called replacement Stego. Now, let's say that the message I want to hide is simply the word secret, and I want to hide it in a bitmap image. So like an image of a dog or something like that. Each pixel has a 7-bit binary mapping to it, and that indicates the color. So the first 3 bits in the color mapping, that's going to be your primary colors. Like when you're mixing red and blue to create purple, or yellow and black to create some brown. Those bits on the left, especially the first 3 or 4, those are the most critical to the actual color. The bits on the far right, like the lowest 2 bits or 3 bits, if I make changes to those bits, it's unlikely that your eye is going to detect the color change just because we don't have great vision as humans. Now, if you're looking at some super high-end res photo taken from a digital camera and you modify the lowest bits, the color is going to be so detailed, you're not going to notice a difference. Now, you could degrade the quality. If you get too greedy and you start taking the lower 4 bits of every 6 or 7 bits, now you're taking too much. You're going to degrade the quality of the image so much that it's going to affect what the user sees. But let's set up a scenario. Let's say you're a parent and you take a look at your kid's computer and you see there's a photo of the family dog. That's the only photo you get to see. So you can't even compare that photo to another version that maybe wasn't steganographically altered to see if it's been degraded in quality. So remember that. You don't even know that something's hidden in there. I'm just going to show you how it works. So you could see that we've got secret over there, and I've got the binary representation from the ASCII hex mapping. That's the binary representation of each letter. And what I want to do is hide this data inside this bitmap image without degrading the quality. So of course we'd encrypt it first. We wouldn't just hide the data as is. We'd encrypt it, but I'm making this simple. And what we're doing here is we're taking the first 3 bits and we're hiding it in the lower 3 bits of that 6 or 7 bit field. Now, if we go back a slide, it was 011. We changed it to 010. So effectively, we've only modified the lowest bit. You're not going to see a color change that way. Then we go and replace the next lower 3 bits with 100, and then the next one, and then the next one. So you see how we're hiding the message piece by piece inside the lower bits of each pixel value to not degrade the quality too much to ruin the image. That's basically how it works. It's just one example. Other examples, we can hide it in Slack space and stuff. There's all kinds of things we can do, but that's pretty sneaky, right? How you can go in, encrypt a message, hide it in a host file. This could be an MP3 file if you want. If you take an MP3 file and it's 256 bit quality, kilobit per second bit quality, and we reduce that to 192 kilobit per second bit quality, most people would not detect the change in the ear when in fact we're now hiding data in the lower portions of each of the sections of data. So I think that's actually, Dave, at the end of what I wanted to talk about here. I know it's a lot of information, and I know some parts were smoother than others.
I think it's great. I think a lot of people might be more interested in hashing. So I think just for everyone who's watching, please put your comments below. Do you want more hashing detail? Because I think, Stephen, I've seen so many misunderstandings about hashing. So perhaps you can do like a detailed one on hashing. Yeah,
I think one thing we could do is take a look at hashing in more detail. Maybe not go into like the depths of how the algorithm and the math works, but I can put up an image that shows you like the registers that are used, the initial block size, how that factors in. And we could use that to talk about something like hash length extension attacks and actually see an example of how you would go and go after an implementation that's insecure.
And maybe like pigeonhole, stuff like that, if you'd like to cover that.
Yeah, we can certainly take a look at anything.
Yeah, that'd be great. So just for everyone watching, please put your comments below. Do you want to see more about hashing? But Stephen, I really want to thank you for putting this presentation together. I mean, that's a lot of information. It's like a whole tutorial that we get for free. So I really appreciate you doing it.
Yeah, it's thanks. It's hard like to pick what you're going to talk about with crypto. So I tried to pick some sections that I know that are like very common out there. And again, when you're trying to take on a topic like crypto, you don't quite know each person's level of mathematics and where they lie. So I'm trying to simplify things in such a way and show you examples without getting too complex on things so it's digestible for folks. So hopefully I didn't mess that up too much and you get some value from it. Feel free in the comments. If you want to pick on me about my math skills or my drawing skills, you're not going to hurt my feelings. I have no ego. I'm not trying to say that I'm some brilliant mathematician, but just wanted to shed some light on some cryptographic issues. And also, if I made a mistake anywhere, let me know. I'm happy to correct that as well. But I think I got through everything, but sometimes it's hard to not miss in this wording somewhere.
And just for everyone's benefit again, can you remind us about your YouTube channel?
Yes, thank you. It's Off by One Security on YouTube. I do streams every Friday. I have a lot of guests. Like, obviously, I don't know when this video is getting posted, but I'll have just had Chompy on. I just had just a lot of amazing folks who share their knowledge on fuzzing and how they approach vulnerability research. And then, of course, branching out to different things like web application security, crypto and blockchain and smart contracts and just all over the map. So I also have a Discord server that you can check out. And it's an open one. There's a couple thousand members right now. Very friendly community. But I brought that up because there's a channel on there for requesting streams and requesting certain guests. And of course, I can certainly try and accommodate that if possible so we can cover topics that you're interested in.
So for everyone watching, please go and show the love. Go and sub to Stephen's channel. He's trying to grow it. Stephen, again, thanks so much.
Yeah, thanks, David.